Okay, we're back with calorimetry extra problem number 1. We can see here, I filled in the heat gained by the calorimeter or heat lost by the metal. Now we know that since the calorimeter is a system that is closed, that we're trying to insulate from the outside world, that all of the heat that the metal loses is gained by the water in the calorimeter. Because we've tried to keep any heat from escaping to the outside world by using styrofoam. And we've also tried to keep any heat from outside world to come into the system. Styrofoam is hopefully going to insulate our system. So we're assuming all heat lost by the metal is gained by the water in the calorimeter. So if we plug in to our equation here, all the heat that the metal loses goes to the water in the calorimeter. Negative Q of the metal equals Q of the water plus Q of the calorimeter. Negative Q of the metal, well, if I say negative and then I put in the Q of the metal, which we found to be negative 3,170 joules, then what do I get? Well, a negative is really a positive. So the negative Q of the metal is actually going to be a positive 3,170 joules. That is a tricky moment in calorimetry, and you want to stop and think about that. Make sure you understand what just happened there. That's equal to the Q of the water, which we don't know, plus the Q of the calorimeter, which we found to be 20. I use scientific notation here to show two significant figures. Right here I'm just going to show you that it really is. So I need to subtract 20 from both sides. Now notice over here, when I do this subtraction, this is not significant in the ones place. We have 3 significant figures in the Q of the metal. So even though this is significant in the ones place, this is not. So I'm going to have to round to the tens place when I finish this. So 3,170 minus 20 is going to be 3,150. Only 3 significant digits left because we'll have to round to the tens place here. Joules. So Q of the water equals 3,150 joules. And I'll fill that in here on the chart. 3,150 joules. So now we can find the mass of the water that was in the calorimeter. I'll erase this part so it fits. We're looking for mass of the water, so we'll say water, purple colored. And we have Q of the water equals its mass times its specific heat times change in temperature. We found the Q of the water to be 3,150 joules, 3 significant digits, equals the mass of the water, which we're trying to find, times the specific heat of water, joule per gram, degrees Celsius, times change in temperature of the water, which we found to be 2.0 degrees Celsius. So now, if we solve for mass like this, mass of the water equals 3,150 joules divided by 4.184 joule per gram degrees Celsius times 2.0 degrees Celsius. We find joules cancel here, degrees Celsius cancels here, and we have gram in the denominator of the denominator, which makes it really in the numerator. Mass in grams is exactly what we want, so that's perfect. And I find mass here to be 380 grams. So there were 380 grams of water in the calorimeter. We have to round that to 2 significant figures, which it is because there are 3 here, 4 here, but only 2 in our temperature reading. So we have to round to 2 significant figures since we're multiplying and dividing with these numbers. We just count them, round to 2, since there are 2 here. And that's our least number. All right, so we found our goal here, 380 grams of water in the calorimeter. And it asks us to continue looking at this problem and ignoring the calorimeter. Just like we did in our lab experiment, ignoring the calorimeter. Is that a good idea, a valid point? Will it change our answer very much? Well, let's see. If we ignore the calorimeter, then we would find the heat that the metal lost to be equal to the heat that the water, we all know water is H2O, right? The heat that the water gained. So we're going to ignore that calorimeter and just do it this way. So I will, instead of using my 3,150 joules that I found by including the calorimeter, I'm just going to say 3,170 joules is the heat that the water gained from the metal. If I do it that way, and I just plug in here, and a Q equals MC delta T for the water, 3,170 joules equals mass of the water, which I'm trying to find, times specific heat of the water, 4.184 joule per gram degrees Celsius, times change in temperature of water, 2 degrees Celsius, with two significant figures. Then I find the mass of my water to also be 380 grams. Significant figures cause the effect of the calorimeter's heat absorption to be negligible. So we get the same answer if we include or ignore the calorimeter. So it's perfectly valid for us to ignore the small difference that the calorimeter makes, because significant figures cause it to round out anyway. If we had a more precise thermometer, we might be able to make the calorimeter make a difference. And now I'll stop the video and come back with extra practice calorimetry problem 2.